In this board, we are first seeing piecewise linear transformations. Okay, see the word piecewise. Okay, something apart upon a part of the image, a piece of the image. It means some parts. We are selecting intentionally few parts, and upon those selected interested parts, we are applying linear transformations. This is the meaning of this one. And for this piecewise linear transformations, we have two types of piecewise linear transformations. First is contrast stretching, second is intensity level slicing. Okay, now what is contrast stretching? Contrast stretching means uh, uh, we know the stretching. Stretching means we are enlarging or shrinking something. So here, on what part of the image we are applying all the operations and the transformations, whatever the process we are applying upon intensity levels, right? Then contrast stretching means we are expands, means enlarging the range of intensity levels in an image. Okay, so some range of intensity levels we are expanding, that is called contrast stretching. And after doing this, expanding some range of intensity levels, it spans the full intensity range of the recording medium or display device. Means it is occupying, it spans full intensity range of the recording medium or display device. For this, see an example here. See this example. See, this is this is the intensity levels graph, and these are the input intensity levels at various intensity points, and this is the output level, output intensity level. And if we applied this form of transformation, this is the transformation function we applied, so that the resultant curve we got, the graph we got after applied the transformation function. So actual input is this, input image is this one. Upon this input image, okay, we applied, see, this is low contrast image. It is not a normal or a high contrast image. It is a low contrast image. Low contrast image. Upon this low contrast image, we applied this transformation. Then we got the resultant contrast stretched image, this one. See the difference of this one. Okay, and upon this, so from this to here, we got we applied a linear transformation piecewise. Then we got this contrast image, stretched image. So from the original input low contrast image, this is the stretched image. Okay, and from this, if we applied thresholding, then after applying thresholding, the resultant image is this one. So this is the final image, which is uh, uh, which is uh, which is stretched and threshold image. And Next one is intensity level slicing. This intensity level slicing means, see here, this is the slicing. So we are slicing means dividing into parts, but here it is some interested part we are highlighting. Okay, some interested intensity, specific intensities in an image. Okay, specific range of intensities which are our interest ones. Those specific range of intensities are highlighting. This is called the intensity level slicing. See here, this is the example. So see, this is the original image. This is the original image. Upon this original image, actually it is a aortic angiogram. Okay. So for this image, we are selected this part by the transformation function. Okay. Now this specific range of intensity values of this image from A to B, this is the A and this is the B. From A to B, we want to highlight this interested specific range of intensity values. Okay, upon this range of intensity values, upon this part only, we are showing interest. Then we applied slicing. After applying slicing, this is the resultant highlighted part we are getting. So this is the result of slicing transformation. See the difference of this one and this one. Okay, after slicing transformation, this is the image, and after grayscale image of this one, this is the grayscale image of the sliced transformation image. Okay, and why we highlighted means this is an application. It is showing the major blood vessel, the shape of the flow of the contrast medium. Okay, so major blood vessel which study the shape of flow of the contrast medium to detect a blockage. Where is the blockage happened in the blood vessel? For that purpose, we highlighted this part particularly. And why we are converted this into grayscale means we are measuring the actual flow of the contrast medium as a function of time in series of images. Okay, so when we take in the actual flow of the blood, then by time to time, where the flow is happening and where the blockage is happening. That's why here we take in the time in a series of images. This is the application of the slicing transformation operation. Now, another type of slicing, which is bit plane slicing. It is already saying bit plane. So bits are laying placed as a planes. And so this is the 1/8 bit plane, each one representing a bit, and this is the least significant bit and this is the most significant bit. Okay, total 8 bits, 1 byte. So this is the representation of the bit plane size slicing. Then where we are applying, how we are applying. So slicing means we already know slicing means some range of interested intensity values we are highlighting. So this is the input image, low contrast image. Then we placed this input image into bit plane slicing. This is 1, 2, 3, 4, 5, 6, 7, 8. Okay. So we applied 8-bit grayscale images of the size 500 into 1192 pixels. So all these are the bit planes. Then see the difference, contrast difference between the input image and the output image. Some intensity values are highlighted, okay, by the bit plane slicing operation, and which are highlighted means, see this here you can easily find out this is the these are the areas highly we concentrated, so these are highlighted within the output image. Third, the main topic, important one, which is histogram processing. Okay, so this is, suppose, see, this is the sample example image. Okay, input image. For this image, the histogram generated after processing is this one. So the histogram of this image is look like this. Okay, these are the values. What kind of values I'll explain now. So actually what is histogram and why we are plotting this histogram graph means, we discussed at the start of this board, we discussed spatial domain. So histograms are the basis for spatial domain processing techniques. We have seen bit slicing, spatial domain techniques like those. So histogram is the basis for all those spatial domain processing techniques. And by using these histogram manipulations, we can effectively enhance our image. So the importance of the histogram techniques and plotting the histogram, because for the effectively for image enhancement, for the image enhancement, we are taking the histogram plotting graph, and these histograms are simple to calculate in software, very simple calculation it is taking, and economically the hardware implementation is also very simple, and these histogram tools are in real time very popular ones. And then how to draw and what type of values we are plotting in the histogram. So the histogram is it acting as a graphical representation. I already showed that graphical representation. See, this is one histogram, this is another type of histogram, and this is another type of histogram. The histogram graph is like this. Then uh, the graphical representation includes the tonal distribution in a digital image. What is meant by tonal? So tonal means it is the range of values. Those values are difference between the lightest and the darkest areas of the picture. Okay, so tonal values are representing, giving the range of lightest and the darkest values. They are showing the difference. By taking those differences, we are plotting the graph. Then we are enhancing the image, and the number of pixels of each tonal values are we are plotting in the graph of the histogram. And by looking at the histogram for a specific image, a viewer will be able to judge the entire tonal distribution at a glance. So, by seeing the histogram, the entire what are the brightest pixel values, intensity values, and what are the light, thick, thinner, all those we can easily see within the histogram by seeing the histogram plot. And what are the applications of the histogram where we are using most commonly and popularly? We are using these histograms in a digital cameras. Okay, many modern digital cameras. And photographers can use them to show the distribution of tones captured, which part is lighter one, which part is darker one, and how to remove darkness and everything. Image details has been which image details are lost within the image, and which are blown out, highlights are blacked out, shadows, everything, all the details. The photographers and the viewers can easily understood by the histogram. And within the histogram, uh, plotting the graph, the number of pixels in the image are always in the vertical axis, and particular brightness, whether it is dark or light, means the tonal value is on the horizontal axis. So here it is the horizontal axis and it is the vertical axis. This axis giving the values of number of pixel values, and this axis giving the tonal values, how much brightness, how much darkness, all those. So to process this one, we have so many algorithms. Those algorithms I'll show in after this topic, after this text. Uh, then then uh, in the digital editor, we are using so many softwares to edit the images. Then users visually adjust the brightness. We are adjusting the brightness within the editors, with digital editors. Those are the editors who the photographers using. They are adjusting the brightness of the each pixel value, and they are showing dynamically, they are displaying dynamically the resultant adjustments which are made within the photo. Okay, behind this, the algorithm, the equation is histogram equalization. This is one algorithm behind this adjustment of uh, brightness enhancement of the image the photographers using. Okay, so this histogram equalization is an algorithm which is popular one to improve the brightness of the picture, and also for the contrast, and the contrast values also we can obtain by this histogram equalization algorithm. This is one type of popular histogram algorithm, one type. And so, if we see within the computer vision, field of computer vision, this histogram is very useful tool for thresholding, where we are applying this thresholding. How this histogram useful tool for this thresholding means, this histogram giving the graph is consisting, we are already seen, the graph is consisting peak values and something like valleys values. Okay, then the threshold value we can take from those peak values and valley values, the graph given by the histogram, we can use those threshold values for edge detection, image segmentation, and co-occurrence of the matrices. For these operations, uh, we can take threshold values from the histogram. And see, these are the popular algorithms: histogram equalization, histogram matching, local histogram processing, and using histogram statistics for image enhancement. These four are the important histogram operations. Now we will discuss what is histogram, how to calculate, what is the mathematical equations behind that, and what are the um, resultant ones, equations, algorithms, everything. Now see, histogram processing. What is histogram processing? How we are processing the histogram. The histogram is defined with the model formula h of rk is equal to nk. Okay, here h representing the histogram. Okay, small letter h representing the histogram, and we already know small letter r is representing the intensity value of the pixel, and for which pixel intensity we have so many number of pixel values. Among the number of pixel values, intensity values within the image, kth intensity value is representing with the r of k. So r of k is the kth intensity value. So kth intensity value, uh, for the kth intensity value, we calculating the histogram that is equivalent to n of k. Here the n is representing the number of pixel values and k is representing particular kth intensity value. Okay, so at the kth intensity value, the number of pixel values, h of rk is equivalent to n of k. This is the histogram equation. And normalized histogram equation is equivalent to always at the kth intensity value. This P is representing the normalized histogram, which is equivalent to n of k, number of pixels in the image with the intensity r of k, divided by mn. I already told you the mn representing the size of the image. Image is representing in a matrix form, and the matrix form size we are taking two-dimensional m by n. So mn is the size of the image value, the intensity of the k, kth intensity pixel value. Now I'll show some different types of intensity histogram values for various images. So for the dark, see, this is the dark image. For this dark image, we can get the histogram graph in this way. And this is the light image. See, compare with the previous one. Then for this light image, we will get the histogram values in this way. And see, this is the low contrast image. For this low contrast image, these are the histogram values. And this is high contrast image. For this is the histogram value. See and observe for the low, dark, and for the light, and for the low contrast and for the high contrast. See, observe the difference between histogram values. Now see the other the histogram algorithm. Okay, that is histogram equalization algorithm. What we will do with the histogram equalization? We know the histogram is something look like this. So all these are the intensity values of the image. Then the range of intensity values, the intensity levels. So here in this histogram, the level of the histogram is here, and for here this is the level of the histogram, other level of the histogram, this is other level of the histogram, again it is another level of the histogram. So we have a different types of intensity levels. So the intensity levels in an image may be viewed as a random variables in the interval 0 to L minus 1. What it meant is we are taking number of intensity values to plot the histogram. Those number of intensity values, suppose we are taking from starting to 0 and maximum we are denoting, so the minimum value, the initial value we are denoting with the 0, and the maximum value we are denoting here with the L. So whenever we start with the 0, then we say the range between 0 and L, it should be 0 to L minus 1, because we initiated with the 0. So whenever we start with the 0, obviously the maximum value always should be minus 1 lesser value than the maximum value. So here we are taking the intensity value levels as a random variables, and we are taking in an interval 0 to L minus 1. Okay, these are the random variables and the intensity levels. Random variables means all these are random variables, randomly selected variables. These are not in a uniform fashion. This is not a uniform fashion. Here it is growing up and here it is coming down. It is not a linear fashion. It is not a uniform fashion. There is a up and down curves. So random variables. And then for the histogram equalization, we are taking probability density function. What is this PDF? Probability density function. I'll explain. First, for the histogram equalization, we are taking PR of R. We know R is the intensity value of the input image, and PR is the probability density function for the input image, and PS of S. This is, we know S is the output intensity values. So the probability density function for the output intensity values is obviously denoting with the PS, because P is a probability function. We know the probabilities. Some likelihood of outcomes the probability function gives. Probability density function means, here see, probability density function PDF is a statistical expression. We know the probability goes under the category of statistical mathematics, statistics. So it is a statistical expression that defines a probability distribution. Here also we are distributing the intensity values. Okay, so the intensity levels are distributed. So we take in this statistics equation, we used this probability function because PDF is a statistical expression which is giving probability distribution for a discrete random variables, okay, as opposed to a continuous random variables. Got the point? So for the histogram equalization, we have a random variables, and we are opposing the continuous random variables. It is a distribution among the discrete random variables. So obviously we have to select the equation, the mathematical equation for the histogram equalization, the probability density function, which is satisfying all these needs for the equalization. And what you thinking about the histogram equalization? See the word equalization. So this is the histogram looking like this, up and downs, curves, different types of distribution from the random variables, intensity values. Then we are going to equalize, okay, giving some uniformity for this one. That is the operation under histogram equalization. So the probability density function giving the difference between discrete random variables, and you can identify exact value of the variable. Okay, this is the purpose of the probability density function. It is differentiating it is differentiating all the discrete variables and identifying exact value of the variables. When we want the likelihood exact values within the outcome, we have to use probability, and and within the probability, here we want to extract the values of the variables which are identical, uniform from the discrete random variables. Here we used probability density function. Okay, so see, see this. This is the arbitrary probability density function, and here the range is 0 to L minus 1. R is the input intensity values, and this is the input intensity value, PDF, probability density function. And after applying the transformation upon this, this is the output intensity levels histogram, which is see, observe here, this is equalized. See this. This is equalized. So this histogram is equalized here. Got the point? So we applied some transformation. And here, see, this is the range of input 1, but we got this one 1 by L minus 1. So this is the histogram equalization output, and this is for this input. Now look at the histogram equalization formula. So a transformation function we applied upon the input intensity levels. So the function is T of R, which is giving the output intensity values S. Always here always we used S for the output intensity values, R for the input intensity values. And the range we know 0 to L minus 1. So 0 is less than or equal to R is less than or equal to N minus 1, L minus 1. Then we are saying T of R, the transformation function upon the input intensity values, is a strictly monotonically increasing function. Okay, what is meant by strictly monotonically increasing function? Monotonically means in a similar singular fashion it is increasing, and strictly with so T of R, the transformation function upon R is a strictly monotonically increasing function in the interval we know 0 to L minus 1. And we are defining the transformation function. So from this A postulate, the range of transformation function is also 0 to L minus 1. Same applies for this. And for R values, means the intensity values, 0 is less than or equal to R is less than or equal to L minus 1. So see other example of this equation. Monotonically increasing function showing multiple values can map to a single value. So multiple values, these are multiple values 1 2 and so on. Here multiple values we are mapping in a single function, strictly constantly increasing function, but here some discrete values are taken. Okay, so all these are multiple values. From this, the strictly monotonically increasing function is a one-to-one mapping in both ways. See, strictly monotonically increasing only, and in the similar way, in the similar shape, monotonically decreasing also, one-to-one mapping. This is the example for the equalization. So this curve should be this histogram, and these intensity values, these range of intensity values are equalized in this way. See and observe the equalization of the histogram. Now the formulas we are applying. Okay. So the formulas for the histogram equalization are very simple, I think, from the explanation. This is the output. S is equal to transformation function of the input T of R. R should be in the range of 0 to L minus 1. And we know T of r is a strictly monotonically increasing function in the interval 0 to L minus 1 minimum value and the maximum value, the interval. And we also know the transformation function is also in the range, in the same range 0 to L minus 1 for the intensity, input intensity values r, which is also in the same range, same interval 0 to L minus 1. So the T of R, the transformation function for the histogram equalization, is continuous and differentiable. Okay, which is continuous and differentiable. See, it is continuous and differentiable. So, and I think you already captured the word differentiable. So, and I think you also captured the word interval. So, within the histogram equalization, we are applying probability density function, which is underlying using probability. And from the interval word, you may grasp the histogram equalization also using intervals, the mathematical background, integrals, intervals, and from here differentiations, differential equations. Okay, integral intervals also you use. And from the differentiable word, I think you also grasp the histogram equalization is using differential equations. In the first year maths, you learned all these integrals and probability statistics and differential equations. So see, this is the histogram differential equation, which is probability of s. See, the differential equation is also using the probability function. You know, this is the probability density function for the output, and with the differentiable equation ds, which is equivalent to probability density function pr of r for the input with the differential equation dr. So if we form the differential equation, then it should be ds by dr, which is this, is equivalent to, whenever we take in this dr, this comes under here, we know that, and this goes to here, we know that. So this is p of r by p of s by s. See, this is the probability function. This is the equation for the histogram equalization. With this, I already told you the integrals we are using in the histogram equalization. So now we are defining the integral equation s is equal to tr, the transformation function, which is the transformation function, which is equivalent to L minus 1, the maximum range, and the integral is from 0 to r, the input interval intensity value, with the probability of r of w dw, differential equation. Okay, and we are minimizing this with the ds by dr. We already seen ds by dr. What is ds by dr? Okay, this ds by dr is equivalent to, so here we applied the differential equation upon s here. Then it became ds, and we applied the differential equation with respect to dr. So both sides s for the s differential ds, and we with the respect of input r, so dr, so we are applying both sides. So here it should be dtr of by dr. So both sides we are applying the differential equation. After differential equation, we will get the integral equation. From the differential equation, we will get the integral equation, which should be L minus 1. We taken out the maximum range, and we minimized this dtr by dr with the d by dr of, we know, t of r from here. So this is this, and we taken this from there to here. So d by dr, and we applied the equation t of r, this one, from here to here. In the place of tr, we written this integral equation, and we simplified this again, which is simply L of L minus 1, the maximum range, and this whole thing is equivalent to probability of R, probability density function of the input intensity levels, P of R. This is simply we got this equation for the ds by dr. Okay. After applying the differential equation upon the both sides of s is equal to tr, and then we, after applying differential equation, we will get the integral equation. Then this is the simplified equation. And now ps of s, okay, ps of s is defined as pr of r multiplying with dr by ds. Okay, and again it is simplified. This dr we are sending to here, so obviously ds by dr, it the equation became ds by dr. So p of r here, which is same, and we are sent this to down further division, so it became ds by dr. Then p of r, and we know the ds by dr from here, which is simply this one. This came from here to here in the place of this. So simply P of R, PR of R is divided by L minus 1 PR of R. Okay, and further we simplified this into 1 by L minus 1, because these two getting cancelled in the division. So PS of S is simply equivalent to 1 by L minus 1. This we got from the histogram equalization. That's why here in the PS of S, the range is 0 to 1 by L minus 1. Now, so we discussed the histogram equalization, how to calculate the histogram equalization. We have seen the formulas. Now see one example, how to apply within those examples. in this integrals and in this differential equations. See an example. Suppose that the continuous, okay, this is the continuous intensity values in an image have the probability density function. So here within the example they are given probability density function PR of R. We know the R is the input intensity values and the probability density function is represented with the PR of R. We know, we already seen this. And for the range, interval range 0 to L minus 1, this is the PR of R function for this range. And if this is not the case of range of the image, so the range of pixels are not in this limit, then 0, otherwise it is 0. So this is the probability density function given. Now find the transformation function for equalizing the image histogram. Now we have to find out the transformation function for equalizing. This is a continuous one. For this we have to equalizing the image histogram. Now see an example. Solve this example. We know S is equal to T of R, transformation function, which is transformation function. And it is defined, the transformation function is defined with this formula. We already discussed this. PR of W L minus 1 dW. In the place of PR of W, we applied the integral, this one. This we applied here, PR of W, this one. Clear? Now see, L minus 1 whole square. This is whole square. So this will cut 1, L minus 1. So remaining is single L minus 1. And 2W here it is the R. So 2W into R. It will become R square by applying integrals. Integrals. So we got as the transformation function. Now this is completed. Now the equalizing the image histogram we are seeing here for this example. Next step. So in the continuous case, they asked the continuous case. S is equal to TR, L minus 1, 0 to R, PR of W. So this we got. And for the discrete values, Sk is equal to TR. This is the formula for discrete values. And here for this we applied Nj by Mn with the sum of j is equal to 0 to k. Total k is the 0 to L minus 1 intensity values. So for the continuous one, we have this histogram equalization, and for the discrete values, we will get this histogram equalization. Now, see other example which is calculating. See the question here. Perform histogram equalization on the 8 by 8 image. Here the M by N, M is 8 the matrix size of the image, and n is 8 by 8 image. The gray level distribution of the image given below. The gray levels are given. The gray level distributions are given. See, the gray levels are represented with the R of K. So gray levels are 8 by 8 matrix. So total 8. 0, 1, 2, 3, 4, 5, 6, 7, total 8. And corresponding number of pixel values P of K is, for the 0 it is 8, and for the 1 it is 10 number of pixel values for the gray level 1. Okay, and for the 2, so corresponding number of pixel values P of K for the gray levels R of K are given. According to these, we plotted a graph first. So number of gray levels are indicated in the x-axis, and number of pixel values are indicated in the y-axis. So this is P of K, and this is R of K. So for the 0 it is 8, and for the 1 it is 10. See, for the 1 it is 10, and for the 2 it is also 10. 2 is also 10. 3 it is 2. 3 it is 2. 4 it is 12. 4 it is 12. 5 it is 16. 5 it is 16. 6 it is 4. 6 it is 4. And 7 is 2. So in this way we plot it. Now, how to perform histogram equalization. First, input values RK and PK. We plotted this graph. Now, based on that, first calculate total number of pixels. So total number of pixels, these number of pixels PK, total number of pixels means 8 plus 10. So sum of all these, see here. So 8 plus 10 plus 10 plus 2 plus sum of all these is equivalent to 64. And next, to perform histogram equalization, first we have to construct a table, and from that table we have to plot a graph. So first we have to construct a table. The table including the number of columns, first column representing gray levels R of K. Sometimes we represent gray levels with the G also. And second column representing number of pixels P of K. This is first column, this is second column. And third column is the probability density function, probability P of n. Next is the cumulative number of the probabilities, and next is the L value, and we calculate this L value here 7 into cumulative number of probabilities. Why here it is 7 means the size of the matrix here is 8, total 7. L is a 7 here. That's why we multiplied this cumulative number Cm with the 7. If it is a 32, Then here you multiply with the 32 and with the cumulative number. Next column is the round off value and next is the number of pixels. Okay, and P of M. What is this P of M? How we calculate this P of M? Means it is the probability mass function P of M. We calculate this how? Means divide pixel value by total number of pixel values. So the pixel value is 8, first one, and divide this pixel value by the total number of pixel values, 64 in this case. So 8 by 64 is the 0.125. This one, P, this one, see. This one, 0.125. So R of K, P of K, P, first one is calculated 8 by 61. Next one is calculated 10 by 64. This one, 10 by 64. 2 by 64, 12 by 64, 16 by 64, 4 by 64, 2 by 64. These are the PM values. Probability mass function PM values. Now calculate the CM. How we calculate this is CM? CM value for the first value, it is same as it is, and to the second CM value we have to combine, we have to add the first PM value and the second CM value. I'll show how. See here, the first value is first one, second value of PM, and third value is second CM. So second value of PM and first value of CM. These two combinedly giving second value, and these two combinedly giving third value, and these two combinedly giving next value, and these two combinedly giving this value, and these two combinedly giving this value. So previous CM value, next PM value, giving total cumulative number. Now calculate L. L is here we are 7 into CM. So multiply all CM values with 7. These are the resultant one. Now round off. So 0.8 means round off value 1. 1.9 means round off value 2. In this way round off all L values. And we calculated round off values. Now number of pixels, the last column we have to calculate for the histogram equalization. So this is the first one. For the first round of value, number of pixels are 8. This one. And this is the second one. For the second, the number of pixel values are 10. This one. And for this, the round of value of third one and fourth one, both the L values, intensity values, the round of value is common 3. So actually it is a second one and third one, this one and this one. So we have to sum up, add these two. So the common number of pixel value is 12 here. by adding this one. And next 1 0 1 2 3 I mean 1 2 3 4 is completed. So next now round of value is the 5, and this is the value of number of pixel values, and next is the 6. So this is the value of number of pixels, and next for these two also the round of value is the same. So we are adding these two and writing number of pixel values. So now we got number of pixel values and we know the intensity values. Now plot the histogram equalization. So total we have 7, 8, 0 to 7, and these are number of pixel values. See, for the 0 it is 8, 0 it is 8, and for the 2 it is 10, and for the 2 it is 10, and for the 3 it is 12, for the 3 it is 12, and 5 it is 12, 5 it is again 12, and 6 it is 16, 6 it is 16, and 7 it is 6, 7 it is 6. This is the histogram equalization graph. So in this way we have to perform histogram equalization, and I'll show you another example here. This is another example. See, suppose 3-bit image. 3-bit image means L is equal to 8 and size is 64 by 64 means it is m by n value. N values are 64. Has the intensity distribution shown here in this table. Rk given, Nk given, from calculated values given. Now get the histogram equalization transformation function for the P of Sk and Sk. And for this, the histogram equalization calculations are these. All of you try these by with this previous example. Calculate all these values, and from this calculations this is the histogram equalization graph we got for this example. Mute, pause the video and see the values, calculate these values, and for those values uh, are those values are actually the values of these pixels. So after histogram equalization of this one, this is the output image and this is the histogram, and for this one this is the histogram. All those values we have seen with the before example. These are the histogram equalizations and output images for those values. Now coming to the conclusion, see, in this board we covered the piecewise linear transformations, big plane slicing, histogram processing methods, and histogram equalization. Okay, we will meet in the next board with the other algorithm of the histogram. Okay, learners.